Jung-Il Kim and Wing Hong Lee. My name is John Kearney. I'm with AMETEK Process Instruments, and I run the product management team, and I'm going to act as the moderator today for today's webinar. I know Wing Hong and Jung-Il are excited to share some interesting and educational information on moisture technologies, as well as best practices for installation and maintenance. So before I turn the presentation over to both Jung-Il and Wing Hong, to introduce themselves and share their content, I just want to cover a few logistical items with everyone. I have started to record the session, and just to minimize the back, let's make sure we do want the session to be as interactive as possible. So if you have a question, you can use the chat feature in Microsoft Teams. If you're not familiar with Microsoft Teams, on your Microsoft Teams window, you'll see an icon in the top right area of the screen that looks like a quotation. You can just click on that, and the chat box will appear on the right-hand side of your screen. Feel free to type your questions in the chat there, and we'll have our speakers address those during the presentation or at the end. Alternatively, you can also unmute yourself and ask your question verbally if you feel more comfortable doing that, and I'd be happy to take questions during the presentation or at the end. You can choose to do either one. As I mentioned, this session is being recorded, and we'll make that available on AMETEK Process Instruments YouTube channel within the next week or so. And the link, I will make sure the link gets out to those who have registered for the event next week as well. As I mentioned, the webinar today is sponsored by AMETEK Process Instruments. We are a worldwide leader of process analyzers and instrumentation, and serve really a wide range of markets, from environmental monitoring to hydrocarbon processing, including areas like refining and petrochemicals. We serve the power generation sector, natural gas, and many others. All of our engineering and manufacturing activities take place at several locations in North America, and we have direct sales and service teams scattered around the globe, as well as an extensive network of sales representatives and sales distributors to support our products and our service with our end users. So you can reach out to us through our website to find your local contact, and be happy to assist you with any application needs or service needs that you may have. With that, I'm going to turn the presentation over to Wing Hong, and Wing Hong and Jung-Il will introduce themselves and begin the presentation. Thank you.
Thank you, John. Good morning and good evening, everybody. My name is Wing Hong. I am the Regional Manager for AMETEK Process Instruments, Southeast Asia. In our presentation today, we will look at applications from the perspective of moisture measurement, the most used technologies, recommended installation and maintenance practices, and then we will do a quick review to summarize our discussion today. Next. Water is an unavoidable impurity of natural gas. If you think about it, water is everywhere on Earth. About 71% of the Earth's surface is covered by water. Water also exists in the air as water vapor, in the ground as soil moisture, and even in our body. In the natural gas system, water is a diluent that reduces the heat value of the gas. In other words, it dilutes the gas. Water acts as a solvent of other impurities like H2S and CO2 to form corrosive acids. Natural gas hydrates is formed when methane molecules, the primary component of the natural gas, are trapped in microscopic cage of water molecule under certain pressure and temperature conditions. Natural gas hydrate can form within gas pipeline as a solid or semi-solid mass that can slow or completely block gas flow. Next. Raw natural gas is a mixture of hydrocarbons, mainly methane, ethane, propane, butane, and pentanes. Its makeup is dependent on its source. In addition, raw natural gas contains water vapor, hydrogen sulfide, carbon dioxide, helium, nitrogen, and other compounds classified as impurities. Natural gas processing consists of separating all of the various hydrocarbons and fluids from the pure natural gas to produce what is known as pipeline quality natural gas. Major transportation pipelines usually impose restriction on the makeup of natural gas that is allowed in the pipeline. That means that before natural gas can be transported, it must be purified. The ethane, propane, butane, and pentanes removed from natural gas, known as natural gas liquids or NGLs, are sold separately and have a variety of different uses, including providing raw material for oil refineries or chemical plants. Glycol-dehydration is commonly used to remove water from natural gas to achieve pipeline quality gas in the processing plant. The process dries the gas down to tens to hundreds of ppm of moisture. Moisture of pipeline quality gas is also almost always measured at sales gas metering station, especially in custody transfer sales gas metering. To obtain very low moisture content of down to less than 1 ppm, required, for example, in low temperature processes like LNG, and in quality required for some NGLs, molecular sieve dehydration is commonly used. Besides these two categories of application, we also see the occasional requirement to monitor moisture in raw gas. For example, in raw gas metering. Next. A little bit of history on the development of moisture measurement technology. Nanotube mirror instrument were the very first widely used process moisture monitors. The operator reads the temperature at the time we see the dew first form on the mirror. However, dried natural gas can present a challenge to this instrument, depending on the natural gas composition, as you can have a situation where the processed gas liquefies before the water vapor condenses. Aluminium oxide sensor first came into the picture in the 1950s. Quartz crystal or QCM sensor were developed in the mid-60s by Esso R&D, later purchased by DuPont, and was first used to monitor moisture in catalytic reformers hydrogen recycled gas. Next. Laser-based or TDL moisture analyzer were developed in the mid-80s by Bell Labs, first used to monitor semiconductor production gases. As electronic sensors gradually replaced tube mirror instruments in the 60s and 70s, most process analyzers were programmed to permit them to display dew point like the previous analyzer. Although none actually monitor that property, volume concentration of water is the data of interest. For example, as an impurity in natural gas supply, only the volume of water a dryer can absorb before it needs to be regenerated. These technologies are the most commonly used technologies for moisture measurement in natural gas, but there are others that we will not cover today, including P2O5 and stain tubes. Next. The quartz crystal moisture sensor is also known as QCM or quartz crystal microbalance. A quartz crystal is sensitized with a thin film of hygroscopic polymer, which readily absorbs moisture and enclosed in a small chamber. The assembly forms the QCM measuring cell, as shown in the picture. The quartz crystal is energized to vibrate at a baseline frequency. Absorption of water vapor by the polymer causes increase in total mass of the crystal, which decreases the vibration frequency. The frequency change is the measurement of the moisture concentration. The hygroscopic film has high selectivity for water molecules, and the absorption process is reversible. This performance is repeatable within 5% of reading. Next. Operation of the system, the basic sampling system, is based on the sequence of fixed interval between a dry or reference cycle and a wet or sample cycle. The QCM is extremely sensitive, capable of PBA detection of moisture and natural gas stream. The sampling system is equipped with an internal molecular sieve dryer and a niche traceable moisture standard. The dryer provides zero reference for the dry cycle. And then the combination of the dryer and the moisture generator provides the built-in verification calibration function. The system provides an accuracy of 10% of reading. Next. The quartz crystal sensors, which is the size of a coin, together with a similar but sealed quartz crystal to serve as the reference oscillator, are located in an oven maintained at 60 degrees Celsius. With an extractive sample system, the temperature, pressure, and sample flow rates are controlled, resulting in more accurate moisture measurement. The system provides a measurement accuracy of 10% of reading. With a reference dryer, the limit of detection is 0.1 ppm. A good balance of performance for applications with the moisture level of 10 to hundreds of ppm. With an additional zero dryer, limit of detection is 0.01 ppm for applications down to 0.1 ppm of moisture content. Next. TDL, or tunable diode laser, also known as TDLAS or tunable diode laser analyzer system, is an absorption spectroscopic technique. The light wavelength emitted by a laser diode has an extremely narrow bandwidth and is dependent on its temperature and the voltage applied. The temperature is kept constant and the voltage to diode is adjusted or tuned to let it emit a narrow bandwidth of light at the wavelength that is absorbed by the gas of interest. In this case, we're discussing moisture. The light energy is passed through the sample gas, and a certain amount of it is absorbed by the water in the light path. The amount of energy absorbed, seen as energy lost by the photodiode, is related to the concentration of water in the sample gas. The line locking of the laser output wavelength is controlled by the feedback of the same light wavelength passed through a sealed reference containing the gas of interest, in this case water vapor. However, line locking is not available in most TDL analyzers in the market. Next. Being a non-contact measurement technique using light, TDL is immune to contamination, has a very fast response time, and has very long-term stable calibration. Laser wavelength for measuring other gases like CO2 and H2S are also available. A dual cell, dual laser analyzer provides measurement of more than one gas type using one analyzer. In natural gas applications, a dual application we have seen more often is a combined moisture and CO2 measurement. The dual can also be configured to measure moisture content of two different gas streams. Next. Accuracy and repeatability is 2% of reading, and limit of detection is 4 ppm. This technology is suitable for applications with tens to hundreds of ppm of moisture content. And heating the measuring cell up to 150 degrees Celsius by enclosing it in an oven enable it to be used in applications with high dew point like raw natural gas by keeping the sample in vapor phase. A third technology that's also used in this application is aluminium oxide. It uses an impedance or capacitance sensor. It is a multi-channel system, and so you can achieve a low cost per stream of measurement. It can measure moisture in non-aqueous liquids. It can its measurement principle is based on partial pressure, and hence requires compensation for any difference between sample pressure and process pressure. The biggest concerns associated with the aluminum oxide are its inherently low accuracy and its reliability. AMETEK does not offer this technology. I will now turn it over to Jung-Yu for the rest of the presentation.
Hi, my name is Jung-Yu Kim. I'm the product manager for moisture and trace analytical products. I will continue the presentation. In discussing installations, let's first look at this very special property of water cohesion and adhesion. Here is a scene after rain, water droplets on leaves. Cohesion is the sticking together of like substances, in this case, water molecules sticking to each other, causes the formation of water droplets. Adhesion is similar to cohesion, but it involves unlike substances sticking together, in this case, water droplets clinging to the surface of leaf. Cohesion and adhesion are caused by hydrogen bonds. In the context of analyzer application, water sticks to the internal surfaces of sampling systems like tubing, pressure regulators, valves, filters, etc. On the other hand, water has high heat capacity. It can absorb a high amount of heat before increasing in temperature. When heat is absorbed, the hydrogen bonds are broken and water molecules can move freely. This is readily observed in sampling systems where sample temperatures vary with ambient temperature conditions. Water stuck to the internal surfaces of the sampling system is released or dissolved with an increase in ambient temperature. And this is shown in a pattern and variation of reading between day and night. This slide shows a test done by O'Brien that manufactures sample lines that show moisture weathering of various grades of sample lines. Electropolish with fused silica had the fastest wear-up time. Next was the electropolish by itself, followed by commercial grade with fused silica. The longest wear-up time was regular commercial grade tubing. The fastest wear-up tubing was the one that had the smoothest surface, meaning the least internal surface area, since during wet-up, the internal surfaces get populated with moisture before the actual moisture reaches the analyzer. This slide shows another test done by O'Brien that shows moisture dry down of various grades of sample lines. Electropolish with fused silica had the fastest dry down time. Next was electropolished, followed by commercial grade with fused silica. The longest dry down time was regular commercial grade tubing. The fastest dry down tubing was the one that has the smoothest surface, meaning the least internal surface area, since during dry down, the moisture on the internal surfaces have to be removed before dry gas reaches the analyzer. The best practices in designing sample systems are minimizing the sample system by reducing the internal surfaces. This can be achieved by shortening the distance between sample probe to the analyzer, making the sampling system smaller and fewer by using necessary components and reducing the number of fittings. The speed of response on the sample system is greatly dependent on the sample gas consumption or the flow rate through the sample system. So increasing the speed of response can mean wasting more sample gas. Heated sample lines mean the sample gas is less susceptible to ambient temperatures and reducing the possibility of moisture sticking to the internal surfaces. Tests have shown that the optimum temperature to maintain for moisture is 60 degrees C. Any further increase is just wasted energy. As previously stated, sample line length should be as short as possible. We are often asked, what is the maximum line length an analyzer can handle? There is no maximum sample length. As in the sample line length increases, the internal surfaces increase, and more heating is required to keep the sample system heated. And of course, the speed of response increases. This means that it is best to locate the analyzer and the sample system as close to the sample takeoff point as possible. Using a small diameter sample line reduces the internal volume, thus the speed of response. 1/8-inch line typically has 7.8 times less volume than 1/4-inch sample line. Using electropolished tubing means a smoother internal surface, which reduces the surface area water molecules can adhere to. Gas is compressible, so higher pressure means more gas molecules in the sampling system. More gas molecules in the system is equivalent to a larger internal volume. So pressure reduction should be done as close to the sample probe as possible. Paramount when designing a sample system is to eliminate dead legs. Dead legs are unpurged volume that can be purged before sample analysis or volume that cannot be purged. Dead legs that cannot be purged should be avoided. Dead legs will accumulate moisture and release moisture, especially due to turbulence in the sampling system caused by changes in pressure and/or flow. Sampling components such as probes, filters takes 3 times this internal volume of sample flow for it to be adequately flushed before a representative sample reaches the analyzer. Also, components like pressure gauges are a dead leg. So eliminating the sampling system to only critical components is especially important for low ppm moisture measurement. Union, tees, reducers, and any other similar components adds to the total internal surface area and increases point of leak. So their usage should be limited. Do not use needle valves or rotometers upstream of the analyzer. Those components restrict flow and causes a pressure drop. Depending on the components, they can cause dead leg and or be a source of moisture intrusion. In order to increase speed of response by increasing overall sample gas consumption, installing a bypass flow right at the inlet of the analyzer is recommended. This bypass leg can also be used to trouble higher than expected moisture readings. Moisture reading decreases when increasing, when increasing bypass flow means that moisture is added by the sample system. Moisture reading increasing when decreasing bypass flow means moisture is added by the sampling system. So this is a very good way for debugging higher than expected readings. For maintenance, if necessary, zeroing of the analyzer should be adjusted with dried sample gas to give the best results that also take the background gas into consideration. A emulsive dryer can be used to dry down the gas. Moisture span validation is more challenging. Bottle standards are convenient and is always used for impurities other than moisture. Due to the cohesion and adhesion properties of moisture, the use of bottle standards should be avoided. In a moisture standard bottle, the water molecules will stick to the internal surfaces of the bottle, pressure regulator, and all other components of the delivery system. Also, heat frees up stuck water molecules. So the moisture content of the standard gas is greatly affected by the ambient temperature conditions where the validation is being carried out. Therefore, it is best to use bottled moisture standard for sanity checks and not for actual calibration of the analyzer. As discussed earlier, the QCM analyzer is equipped with internal mold sieve dryer and a NIST traceable moisture generator to support the analyzer, providing 10% accuracy. The verification calibration feature can be executed at any time and set to automatically calibrate on a regular basis.
Jung-Yo, can I interrupt for a minute? There's a couple of questions.
Sure.
The first one that came in, Jung-Yo, was does the outlet of the analyzer need to be at atmospheric pressure? And if that is the case, would having a needle valve after the analyzer be a problem?
Okay, one thing is, first of all, I don't see why a needle valve is required at the outlet of the analyzer. That's one. I don't see any reason for it. Second, if you were to put a needle valve at the outlet of the analyzer, what it would do is it will create back pressure. Whether the analyzer can handle back pressure and how it handles it is dependent on the different technologies. For example, QCM analyzers are first designed to be vented to atmosphere, but due to conditions that due to hazard conditions where the analyzer has to vent to a flare that is pressurized, we don't want back pressure, all the junk in the exhaust system going into the analyzer. So you have the option to put a back pressure regulator that can be set at 15 degrees PSI. So when a back pressure regulator is installed, there is back pressure compensation. So the reading compensates for the back pressure.
Okay, and
the
motivation for the question was asked since we're not to have any flow control before the analyzer, that was the reason for having a valve downstream of the analyzer in order to be able to set flow.
Okay. Most analyzers that I know of, except for I think aluminum oxide, where you can set the flow, or you have to set the flow. With the exception of aluminum oxide, all other analyzers have flow control within itself. So you just have to provide the required sample pressure, and it will do the rest. So for those analyzers that can control, that does control the sample flow by itself, there is no need for any flow control device because it does it by itself. But on an aluminum oxide probe, yes, you need to have, I think one of the things is to install a needle valve to control the flow to it. I've seen some designs like that. But most analyzers do not need flow control, as long as you provide the required sample conditions, the analyzer works fine. I hope that answers the question.
Okay, and I think a couple of slides ago you were talking about zero validation, and a question came in. The question was, can we use plant nitrogen for zero validation?
Okay, plant nitrogen in itself is, I think, has a very wide range of the level of impurities inside, meaning it depends on the quality of the plant itself. Semiconductor plants or air separation plants that supply nitrogen, oxygen, argon to semiconductor plants, they really remove impurities, in most cases down to 10 ppb or less before it is even supplied. But as a safety, they still install purifiers to remove moisture. Plant air separation plants that are next to or used for industrial, oil industry or any other industrial application, they don't remove moisture down to low levels. It all depends on what the customer is asking for. So I think plant nitrogen would at best be considered 5.9 purity gas. 5.9 purity means there is at least 10 ppm of impurities in the nitrogen. And if you, let's say, roughly divide 10 impurities that are in there, it's usually 7 or 8. It will roughly come down to a little bit more than 1 ppm of moisture. It can vary, but let's say 1 or 2 or 3 ppm of moisture you would expect in the best case plant nitrogen. So it depends on what you are using that plant nitrogen for. But if you are using it to zero on analyzer, it can be questionable, meaning it depends on the detection limit of the analyzer. So if the analyzer has a detection limit of 4 ppm, I guess it would be fine to use nitrogen that has a moisture content of 1 or 2. But if your analyzer requires a zero gas that is much drier, then it would not be that you would be using the wrong gas. You need extra drum. I hope that answers your question.
Okay. Also from the slide, a couple of slides ago, you were talking also about calibration bottles or standard bottles. There's two questions on that, two different attendees. The first question is, and this is probably for either you or Wing Hong, where do you recommend buying a moisture standard bottle?
Okay, what I would say is moisture standard bottles are notoriously difficult to maintain the, let's say, maintain the accuracy or maintain the level that is certified. because of the properties of moisture. Just as a side information, I had earlier mentioned that I am also product manager for trace analytical products. Those are GCs that measure hydrogen, CO, CO2, methane, and we use standard bottles. And those standard bottles are actually easier to make because the properties of those impurities are not as bad as moisture. But we have used multiple vendors, and supply from multiple vendors can be inconsistent. So we test out the bottle, and sometimes we do have to reject it. So if that kind of simpler standard bottle manufacturing is that inconsistent, I would really question the manufacturing of moisture standard bottles. So I cannot say which one is good or not, because even the better ones do screw up time to time with non-moisture bottles. I hope that answers the question.
Thanks, Daniel. This is probably a related question around that topic. The question is usually how long are moisture standard bottles valid for? And what other methods do we have to validate moisture readings? So that's, I guess, a two-part question.
Yeah, with regards to how good they are, I think it would really depend on the quality of the bottle and the way the bottle is stored. When I mean the quality of the bottle, as mentioned, internal surface area matters. So depending on how the quality of the bottle, meaning whether it has an electropolished surface, which is the highest quality bottle, or a bottle that is not electropolished. So if it is bottles that are lower quality inside, because you can't really see it because it's internal. So if the bottle quality is of higher standard, I think the storage would be longer than a bottle that is of lower quality. That's all I can say. There is no standard. I'm sure the manufacturer might also state the longevity, but it really depends on the quality of the bottle and how you store it. I hope that answers.
Yeah, and the second part of that question, Jung, was what other methods are available that we have to validate moisture readings?
There are manufacturers of portable moisture generation systems. I think one that comes to mind, I think, is Standard Scientific. But those moisture generation systems are NIST traceable, and within the moisture generator itself, it maintains very precise conditions to make sure that moisture is generated consistently. So those can be used.
Okay, and then Julian, one final question on, I guess, on this topic around calibration standards in the bottles. The question is, what are the calibration standards for moisture analysis kept in temperature-controlled cabinets? So I think maybe this question is referring to potentially bottles kept in temperature-controlled cabinets, or maybe the moisture analyzer, but that's the question as it's written in the chat.
When I was going through the slide, as alluded to, if the temperature of the bottle or the condition of the ambient temperature of the bottle is kept very stable, it will produce more of a stable result. But whether the accuracy of what the moisture that is being supplied remains, let's say, questionable, because it all depends on also the delivery system to the analyzer from the bottle. But if you want consistent reading from a bottle, you have to keep the condition stable. The thing to one thing is when they yeah, I would say, yeah, okay. That is a good practice to keep the bottled moisture standard stable. That would help to get a consistent reading. But there are other factors, as I said, that also contribute to it because of the delivery system.
All right, thanks, Jang-Il. There's like one or two more that are more specific on the 3050. I'll ask you those towards the end. I'll let you continue with your presentation. Thank you for answers to those questions, though.
Sure. For maintenance, bear in mind that the atmosphere contains thousands of ppm of moisture, and it also depends on the weather and the location, which part of the world you are. Some areas, of course, have more moisture in the air than other areas. Some have really less. So due to cohesion and adhesion properties of water, when the sampling system undergoes maintenance, where a break in the sample system is required, where you have to disconnect the sample line, thus exposing the analyzer to ambient conditions, it is best to plug all wetted surface parts, including vents, to prevent atmospheric exposure of the wetted surfaces or the internal surface areas. This practice will decrease the drying down purge time after the maintenance. After the maintenance, always purge the exposed sample system thoroughly before reconnecting the analyzer. This will prevent exposing the dry analyzer to atmospheric moisture and any other contaminants that might be present in the sampling system. Review of applications. There are three ranges of applications, that tens to hundreds of ppm for glycol dehydration, pipeline quality, sales gas metering. Another application is the low ppm application, usually at the most safe dehydration, LNG or NGLs, and the more much higher moisture, which is the raw natural gas itself. Technology-wise, we covered chilled mirror. That was the first technology available or used for measuring moisture. Aluminium oxide, which was the first widely used technology. TDLAS, introduced as the non-contact technology, and QCM, the first technology to use online verification with the internal moisture generator. Installation-wise, it's best to keep the sample line as short as possible, use 8-inch tubing instead of 1/4-inch tubing, electropolished, heated to 60 degrees C, components and fittings minimized, and do not use needle valves or rotometer upstream of the analyzer or downstream of the analyzer, of most analyzers, I would say. And pressure reduction is best close to the sample probe as possible. That reduces the amount of sample volume that needs to be consumed. And then installing a bypass to increase the speed of response. And zero validation when necessary using zero gas, and make sure you know the quality of the zero gas that you are using if you are planning to not use a dryer. and using bottled moisture standard more as a sanity check than something to actually calibrate your analyzer with. Isolating analyzer by plugging all ports and vents and purging the sample system before connecting the analyzer. Because I've seen a lot of cases where after maintenance, they purge the sample system with analyzer connected. And that introduces moisture and other contaminants, depending on the maintenance that was actually done and how long the maintenance took, and them having to replace a lot of the wetted surfaces. Thank you.
Thank you both, Jung-Il and Wing-Hong, for that. There are a few more questions in the chat that I asked. We have about 15 minutes left in the hour. So just following up on the conversation earlier on validation, the question is, in the field, which would be a valid or quote good method to validate analyzer operation? Because as you mentioned, Jung-Il, earlier, bottles are difficult to keep and maintain. And he was specifically referring to TDLAS technology. So I don't know if you or Wing-Hong could maybe talk about what are some methods to validate analyzers in the field.
I think let me first speak, Wing-Hong, and I'll let you speak. Since you use the word validation, I think, and it's not calibration, as long as you use bottled standard that has constant temperature on the bottle itself and also the delivery system to the analyzer, I think it is a good way to validate. So let's say, for example, if the bottle is, let's say, 100 ppm bottle, and you're reading something closer, 80, 90 or something, I mean, it's a good way to validate whether your analyzer is, let's say, working or not. But if you put a 100 ppm bottle to a analyzer and it's reading below 50 or it's reading way off, then what is questionable and you have to first check is whether your bottle is has constant temperature and your delivery system has constant temperature. And when you have that and you still have low readings, test it again the next day and see if you have consistent reading. If you have consistent reading from the bottle, that shows the bottle itself is outputting that. But whether it is actually 50 or not can be questionable. But it's a validation in the sense that your analyzer is reading consistently. So in a way, it's a form of validation, I would see, because you're not actually calibrating it against that bottle. Wing-Hong, your thoughts?
Yes, I guess what Jung-Il said earlier, you know, about using a fuel moisture generator, that seems like a very good proposal. Although I have not seen one of those. Yeah. Since this is validation, like Jung-Il said, and I guess what is more important is to be aware of the property of water, as we have discussed so far this evening. As long as we are aware of the property, particularly with the cohesion and adhesion, and also about the how the hydrogen bond of the water molecule will react to heat. As far as we are aware of that, then you know, using it as a validation method I think is quite fine. I hope that helps.
Okay, thank you both. Now there was another set of questions that were more focused around the QCM and specifically on the flow. So this goes back a little bit, Wing Hong, to when you were speaking on the technology, and also Jing a little bit, I think, on your sampling discussion on the flow rates and so forth. So one of the questions around that was during the change of the reference and the sample period, the flow is fluctuating and causing a change in the adjusted flow, and was asking for a recommendation on that type of an issue. I don't know if either of you have the offer of some comments on that.
Okay. When the analyzer switches from sample to reference or vice versa, or when you are doing a span or validation, so it switches between moisture generator to reference and back and forth. There is an expected flow disturbance. The amount of flow disturbance depends on how well balanced the three legs are. Meaning, there could be, because the flow is controlled by using a proportional valve and a capillary, which is basically a restriction. Any foreign material in the sample system could partially, let's say, block the restriction and cause flow imbalances. But the beauty of the system is, as long as the flow stabilizes within the last 10 seconds of the cycle, the 30-second cycle, and the flow is within the required flow, which is 50 SCCM per leg, the analyzer is able to get a valid reading, meaning a valid moisture reading. But if it cannot get a stable reading at the last 10 seconds of the leg, you will get an alarm, flow alarm. So you will, the user will be aware and can debug what is causing it. So I don't think you should worry about that imbalance or that turbulence when it's switching from sample to reference, vice versa, or MG to reference, vice versa, as long as you don't get the flow alarm. I hope that answers your question.
Okay, thanks, Jill. And then I guess related to that, and maybe you kind of addressed it there, there was a question around the 3050 OLV specific. So again, the QCM sensor technology and seeing some flow alarm error when the flow was set. So I think it had to do with that fluctuation. I don't know if you have any additional comments there, or you felt like that addressed it.
I think that addressed it. One of the things too, if you get flow alarms during the switching, one best way to first debug the analyzer is to, let's say, remove the capillary that has the fluctuation. And after you remove it, reverse the flow and purge it, cycle purge it, to try to remove whatever might be blocking or partially blocking the capillary, and install it back. If it continues, I think it might be the best would be to replace the set of capillaries. I hope that answers the question.
Okay, thank you, Jung-Il. Thank you, Wing Hong. I don't see any other questions at the moment in the chat. I did just post into the chat just some reference material information there and some links. Do appreciate everyone's time attending today's session. I hope you found the content informative. As I mentioned at the beginning, the session has been recorded and it will be up on AMETEK's YouTube page by early next week, I expect. And I do appreciate all the great questions in the chat that have been asked, and appreciate that interactivity. So thanks for that. That makes the entire presentation much more informative for, I think, the whole audience. So again, thank you for your time today, and enjoy the remainder of your day. And thank you to both our presenters. Have a great day.
Thank you very much for
Bye-bye.
attending. Bye-bye.